It is also used for solving both regression and classification problem. However, it is mostly used in solving classification problems. We saw that support vector machines were initially started their performance back in 1994, and people used them for handwritten digit recognition. Before the emergence of boosting algorithms, for example, XGBoost and AdaBoost, SVMs had been commonly used. Before we have these boosting algorithms, for example, AdaBoost, in which we have a tree structure, and in each tree we have a number of weak classifiers, and each weak classifier tends to perform a classification, and then a combination of those weak classifiers performs makes a strong classifier. So that is a boosting algorithm, right? We will not discussing boosting algorithm here, but to just to give you an overview is that in boosting algorithms such as AdaBoost, we have a tree-like structure in which each tree acts like a weak classifier. A weak classifier means that it is not fully able to perfectly classify the input data set alone. So in boosting algorithms, we have multiple weak learning algorithms or weak classifiers, and the combination of all those weak classifiers make a strong classifier, which acts as a strong classifier to perform classification. So before the emergence of these boosting algorithms, people were mostly using support vector machines to perform classification, because when these boosting algorithms came into being, people started using these boosting algorithms along with other classification algorithms, which further improved the performance and accuracies. But before that, these support vector machines were very much in common, and still they are very helpful in solving and performing different regression and classification tasks. Okay, so now let's make a comparison of a support vector machine with a logistic regression first, just to understand the basic concept of an SVM. So we already studied logistic regression in detail. We studied two types of regression. One was linear regression, and the other was logistic regression. And you remember that in a regression, we basically tried to analyze the relationship between two variables, in which one was a dependent variable and other was a dependent variable. And we saw that in logistic regression, we had a number of infinite decision boundaries. So here is a decision boundary which basically separates the two sets of data belonging to two different classes. And in logistic regression, we don't have any specific rule, or we didn't have a thought through process behind selecting which decision boundary should we select as a separator for the two classes, right? So we were basically making arbitrary decisions in order to select the decision boundaries. Now, if you look at this figure, you will see that on this plane we have two different sets of data. So one is here. If I say this belongs to class 0, and we have another set of data which is here, and this, let's say this belongs to class 1. So we have different data points belonging to this class, and we have different data points belonging to this class here. And we can see that if we have a decision boundary here, then the distance between this decision boundary to this point C is quite big. So this point C here is quite far from our decision boundary. So also, if I measure the distance of this decision boundary from this variable b or this variables a, we will see that their distance from the decision boundary is quite less as compared to this distance c. So now we can be, if I consider this decision boundary, I can be very confident about c, that it belongs to class 1, right? If I consider this set as class 1. But if I move this decision boundary a little bit here, then these points here will start lying on this class. So with a very minor change in the decision boundary, we can have a big impact on the number of classes and the number of data points which are being classified as 0 or as 1. So if more data points starts to lying on other class, then the number of misclassifications in our case will start to increase. So due to this reason, because we have an arbitrary decision in order to select the logistic regression, we have tend to move to some other algorithms in which we are much more confident about our data points. So we can say, or we can summarize that there was some problems in logistic regression due to which we had to move to some advanced level algorithm. And what are those problems are that the logistic regression does not care whether the instances are close to the decision boundary or not. So in logistic regression, we are not taking care of the distances of the data points and the decision boundary, right? We are not taking care that whether the data points or instances are close to decision boundary or either they are far away from the decision boundary. Therefore, the decision boundary it picks may not be optimal. So due to this reason, because it is not taking into account the distance of data points and the decision boundary, so we cannot say that the selection of the decision boundary is an optimal selection, right? Because there is no procedure of selecting an optimal decision boundary behind that. Also, if a point is far away from the decision boundary, we may be more confident in our predictions. For example, the figure I showed you, in that figure, the point C, it was far away from the decision boundary too. So we are much more confident about that data point, which is far away from the decision boundary, that it will belong to class number 1, for example. And the decision boundary, the data points which are close to decision boundary, we are not very much confident about that in our predictions. Therefore, the optimal decision boundary should be able to maximize the distance between the decision boundary and all instances. So this is a very important point with regards to the support vector machine. So just keep in mind that in support vector machine, or in an optimal algorithm in which we have an optimal decision boundary, the important thing is that we want to maximize. Maximize means that we want to increase the distance, and the distance will be between the decision boundary and the instances. So the much more distance we have from the decision boundary to the data points, the more optimal boundary will that be, right? So our target is to have this distance maximized between the decision boundary and the instances, right? Therefore, maximize the margins, and this distance which is between decision boundary and the instance or a data point is normally termed as a margin, right? So we want to increase, or we want to maximize this margin which is between instances and the decision boundary. So maximum, the more greater or maximum this margin will be, and we can say that we have most optimal decision boundary for the separation of two different subsets of data. So due to this reason, because this point number 4 was not present in logistic regression analysis, and we used to add this point in our support vector machine. So support vector machine basically takes care of this point, that the margin between the instances and the decision boundary should be maximized. And this is basically the importance of support vector machine. This is why support vector machine is a very important algorithm, and it's being used in a number of applications.